We are. Okay. All right, with the insults out of the way. Okay, so I'll talk about the dark matter sheet in phase space. First, I'll just sort of explain the concept, what's behind it, talk a little bit about how we currently do cosmological M-body simulations when we want to understand how dark matter evolves over cosmic time. And then just show you how to put some of these concepts together to think of the dark matter as a fluid, how to project it into configuration space to get highly accurate density estimates from outputs of numerical simulations, and show you that it has some very nice properties, and right away suggests of how to improve the current technology we have to do highly accurate simulations of dark matter dynamics. So I'll keep showing different examples from that. Okay. So the dark matter sheet here, all I'm thinking of is when you think about the early universe, dark matter is essentially distributed completely uniformly. There's these tiny, tiny little density fluctuations on it. But at every point in space, dark matter just has one velocity, and it essentially has the same density everywhere. It's only as time goes on, of course, and gravitational instability sets in that can feed off these tiny pre-existing density fluctuations to pull it together. And eventually, dark matter, as it falls together, because it's collisionless, it can pass right through each other. You will have, at one location in space, multiple velocities of dark matter particles, if you want. But the beautiful thing is, it starts out completely uniformly, and there is no extent in phase space in the velocity directions. It's just a single valued function everywhere. Of course, the number of dark matter particles is just gigantic. If we think of a 100 GeV style particle, we would have 10 to the 67 or so in the Milky Way galaxy alone. It's just an extraordinary number, certainly a number much bigger than anything we can fit on a computer. It's also, of course, much, much greater than the number of stars in the entire universe. So ideally, you want to think of the dark matter evolution really as a continuum. In fact, if you want to have about 10 to the 6 particles or so in a little box at mean density today, you would have a box of the length of about 500 meters. And it still would contain about 1 million dark matter particles. So if you want to interested in studying scales larger than 500 meters, which we obviously are, you're very welcome to use a continuum formulation. And that's what's known as the Vlasov-Poisson system, and it is exactly the same system that's also used in studying neutral collisionless plasmas. What we do here is just, it couldn't get any simpler. You describe the time evolution of the distribution function in phase space, in 6-dimensional phase space, and it gets advected in the spatial coordinates through the velocity, and in the velocity coordinates through the accelerations. And it all gets coupled purely through the Poisson equation that derives the gravitational potential from the mass distribution that you have. So we'll keep coming back to the sort of continuum description in this. That it's really, really cold is very easy to imagine because the universe expands so much since the dark matter was made that even if it had relativistic speeds early on, you expanded it by so much, you kinetically cooled the dark matter gas, if you want, so dramatically that even sort of the warm dark matter scenarios we're talking about still potentially of being interest when we talk about the missing satellites and so on, even those particles only have about centimeters per second or so speed, tiny compared to the velocity dispersions you get in fully developed structure like the Milky Way of, say, 200 kilometers a second or so. Key thing to think about is in phase space, what's beautiful about this sheet is that just because of Liouville's theorem, it will never tear, it will never intersect, and it just has a beautiful evolution in 6-dimensional space. So here the one-dimensional analog that I hope you're all familiar with is just a Seldovich plane wave. You have sort of a sinusoidal perturbation in velocity, which then just steepens as time goes on. Essentially, this convergence of material here leads to a higher density in the middle. That higher density enhances the gravitational field, and the wave continues to steepen. And eventually, you get shell crossing, and you start having the same, have multiple streams at one spatial location in it. Now just think about how we usually do this in m-body simulations. We think of little points that are now macro particles, kind of the 6 solar masses, or depending on the simulations you do, sometimes for first stars we have 1 solar mass. That's still 10 to the 55 or so real dark matter particles that you're trying to model. So you have a discrete version of this continuous distribution you have around it. So typically when you did an m-body simulation, there's a lot of people here that have, if you want to ask a question, what is the density at a particular location, what you do is say, okay, let me just pick a volume, and then I count how many particles are in there. I know the mass of the particle, so I know the mass per volume, that's the density. Right, but that's the average density over that volume. And you just never can ask the question of what is the density at this particular location in space. And so all the density estimates that we have and that we use when we do gravitational lensing on m-body simulations, or when we even run the simulations themselves to evaluate the potential, when we have to estimate the density, we have usually crude ways of doing that. And what I want to posit here is actually a very trivial thing that in hindsight becomes very simple. But it took a long time to cook it up. If you sort of think about now the space between the particles, these particles that we follow in the simulations, if you think of them as massless tracers, they just move with the fluid. It's now, they right away tell you, at the beginning, you know how much mass was between 2 points. As they evolve and they get closer, well, the mass is still contained in between those 2 points, because they were faithful tracers of the fluid. And now you know the density in that region. It's just mass divided by volume. So here again, we know the initial mass between 2 particles, and we know the delta x, just going to the neighboring particle. So we know the density everywhere between those 2 points. And that's now really nice, because instead of having an average density, you have the density estimated directly at any given point. The only thing we have to keep in mind is, once we have shell crossing and we have multiple streams in one spatial location, right, velocity, spatial coordinate here, we now have 3 streams contributing to the spatial density here. So I have to estimate the density that comes from taking the distance between these 2 particles, the density from the distance between these 2 particles, and so on, and just sum all the densities, all these stream densities up along one spatial coordinate, and then I get the full true density at that location. If I just look at the stream density itself, you can see it gets fairly complicated, and there's a few more technical things, but it's really that simple. All you have to do is sort of look at the length, or the distance of one particle to the neighboring particle. And so in 2 dimensions, we would now tessellate the 2-dimensional plane just using triangles. We would have a 4-dimensional phase space, and if we take one of these points, it can fold over now, and we have in one region we can have multiple triangles contribute to the density at that spatial location. Right away, it tells you when you fold, you will always go in odd numbers. 1, 3, 5. You fold up this manifold, and in 3D, all that is now you use the 3-dimensional simplex, which is just a tetrahedron, can do the same thing. So now I take all this lattice of dark matter particles in our simulation, I tessellate that entire space with with tetrahedra, always connecting 4 dark matter particles, and know that is my volume. So if the tetrahedron now folds in on itself, it can actually become degenerate for a short time, and one vertex moves through the plane defined by the other 3 vertices. It comes out on the other side. You just went through a caustic in that case. But what you know is, okay, I've got that mass inside that volume. That gives me the density. So I can do this trick now. And all of a sudden get true density estimates at every single point, which now then right away allows you to make images that have no noise whatsoever. There is no noise anymore in this technique. And what you notice is that all the sheets and filaments that you form, all the caustics are phenomenally well preserved. and it's just a completely different ballgame in how to visualize your dark matter simulation. The beauty of this is it needs nothing new. You could do this with a simulation that's 40 years old. If you still just have an output, you can use that. It's just a different way of looking at the same data if you want. But the fantastic thing about it is, because it's defined at every point, what we can do now is do infinitesimally thin slices through a calculation, which we do in gas simulations all the time, but now we can do that in dark matter and measure quantities like the density. Here's the velocity dispersion, an entropy-like quantity, or the number of streams, right? How many of these dark matter streams are actually going through that point? And this is really an infinitesimally thin slice. So you have a very low number of streams, usually just one here in the void falling towards the object, goes up to a million or so in this, at this resolution, with just about 1 million dark matter particles inside the virial radius of this 10 to the 14 solar mass object. And you see all the detailed structure in the filaments that feed the object. Okay. Now the beauty is, if we apply this method at the same time on the exact same n-body data, do one case where we do adaptive kernel softening, the typical thing, essentially any image you've ever seen of a dark matter simulation in the last 15 years or so will have used adaptive kernel softening, an SPH style thing. And on exactly the same data, what you notice is that adaptive kernel softening gives you artificial blobs that are just really not in the data. This is a pure artifact of the way you choose to visualize the dark matter simulations. And so you see here many examples, just comparing the old way to the new way. So you have a lot more contrast, and this is much closer to the true density than this is. So that's nice. So we can make pretty pictures from it. But right away you recognize, wait a minute, if I actually know the density better, that was the thing that went into the Poisson equation to give me the gravitational potential. So if I have a more accurate density, I can get a much more accurate gravitational potential, which gives me more accurate forces, which allows me to evolve my simulations much better. And so let me just walk you very briefly through how a regular particle mesh code works. I mean, most of you know this fantastically well. But just for a pedagogical reason, to then explain of how we can use that to already do very small modifications to current codes and try out better density estimators and see what they do. So what you want to do is you want to just evolve. You say, okay, velocities, you want to update the positions given the velocities. You want to update the velocities given the accelerations. In order to get that, that part is the same for all cosmological codes. All they ever differ in is how they compute the forces. Whether it's a tree code, computes it a different way than a particle mesh code. But let me just walk you through a very basic particle mesh thing of doing that. So you've got the locations of all these particles. You assume they are cubes. This way you can deposit them fractionally on a cubical grid or Cartesian grid in 3 dimensions. So you deposit the mass on the grid. That gives you now this density estimate. It looks awful. Like, it's really terrible because you just assumed blobs that are cubical shape. However, since you integrate twice to get the potential, it's not that bad, usually. And so we end up having a, okay, so we deposit the mass on the grid, we FFT it so, to get the Fourier transform of the density field multiplied with the Green's function, essentially solving in Fourier space the Poisson equation. When we FFT that back into real space, we now have the gravitational potential, which we then can differentiate to get the accelerations, which you then have to interpolate towards the locations where the particles are, so that every particle knows how to update its own velocity. Once it has its velocity, you update the positions. We do this in a leapfrog manner, and that's essentially the same in all codes that you hear about. And you end up with softened accelerations, usually on about twice the grid spacing or so, which is good because we said it was a continuum and not individual points that we actually wanted to simulate. We're not trying to get star clusters evolved. We're trying to evolve the continuous fluid. So the new method that we've devised together with Oliver Hahn and Ralph Kahler we call it TCM, tetrahedron centroid mesh, and it's just the simplest way of taking a particle mesh code and combining it with some of these ideas of the tetrahedral mesh that we had. And so we just start with a monopole approximation. What we mean by that is that ideally we would want to paint the entire tetrahedron onto our cubical grid, our Cartesian grid, deposit the mass exactly. That would be a lot of work because you have to compute the intersections of the tetrahedra with a Cartesian grid. So instead what we do is we say, okay, let's just place a fictitious particle at the centroids of those tetrahedra and use that as the density estimate. But keep everything else the same in a particle mesh code. And there's a few more details of exactly how we do the tessellations. But let me just show a few examples what that does. That density estimate alone is already much better. We now have 8 times more particles essentially sampling the density field. And when we do the simple Seldovich plane wave collapse, here's a standard particle mesh code at 64 cube particles for all the panels, but different force resolutions, going from 128 cube to 1024 cube force resolution, where you see lots of particles sort of starting to scatter off the full line, and the TCM converging much more beautifully, even at low mass resolution with high force resolution, converging well to the expected solution. If we show that in Lagrangian coordinates, it sort of puts the things apart a little bit. You see that TCM, the black is a reference solution, that we converge beautifully to the correct solution, where the traditional method, using high force resolution with not enough mass resolution, always leads to all sorts of two-body effects, particles scattering off and not giving you the correct solution. The tree code is in fact much worse here, because you typically run it with even more force resolution than your mass resolution would allow. Now, using this visualization technique, it's very easy to see any errors that are made in the evolution. And so that's very helpful, much more informative than, say, the particle plots that you may have looked at otherwise, would you not have that technique. Using the new technology gets us also much, much better convergence behavior early on. Okay, and so if we here do a maximum intensity projection of the absolute value of the acceleration, you see right away that the TCM now on top has a much smoother and much less noisy gravitational force, which leads to much more accurate evolution. And in a problem that's been known for at least since the early 80s, when you do hot dark matter simulations with our typical n-body codes, you get lots and lots of artificial fragmentation that is all purely numerical, and all of that is absent in the new technique in doing that. Oopsie. Okay. So that's useful. Things are tricky though, because you sort of start realizing you actually have to resolve that, the evolution of that sheet. And that evolution may be extraordinarily complicated. In particular, in three-dimensional situations, you may get an exponential growth of the sheet because it has lots of room in six-dimensional phase space. And while it never tears, its length or its volume grows dramatically. And so what we've done so far is we already added refinement so that we can follow the sheet in great detail, but it also allows the computational demand to grow absolutely, or very rapidly in complicated situations. And so now let me just sort of conclude, perhaps. We don't have that much time. Just thinking of the dark matter distribution as a fluid being traced by these particles as massless tracer particles that just tell you where the mass was flowing, allowed us to devise new visualization techniques that help us now write much better codes. It allowed us to write sort of this new version that we call tetrahedral centroid mesh to do collisionless n-body simulations. This works both for dark matter, but also in the plasma community. And we've already done some studies on Landau damping and two fluid instabilities or two stream instabilities in collisionless plasmas, and works really nicely there. The one serious drawback is the one I just hinted at, is in situation where the sheet just starts going without bounds, this becomes a very expensive technique. However, it also gets rid of the entire Monte Carlo nature that we rely on in in-body simulation. And I think is a very useful tool for us to understand of whether the converged results that we keep finding are converging for the correct reason or are converging purely out of numerical errors. All right, thanks so much.